everybody, it's Mr. Sheeline here. This is going to be the video lecture notes for the Unit 8.1 set of notes when we're looking at periodic trends. So this is going to be the set of notes that are going to kick off Unit 8. And what we're looking at here in this set of notes is how it is, for the most part, that we lay out the periodic table and making sense as to why it has why it's labeled, or why it is why it is arranged the way it is. So in order to kind of figure out the way it is, we have to cover some terms first. So we have to cover the fact that when we refer to columns on the periodic table, what we're referring to is we're referring to families or groups. So one particular column is a particular family. It's a particular group. That's like alkali versus alkaline metals versus like noble gases. Okay, they are very, or halogens. They're very particular. We give them a name due to the properties that they hold, and we refer to the columns as families. Okay, rows, however, are referred to as periods. So periods are arranged by increasing atomic numbers, and each new period represents the beginning of a new energy level for electrons. So, and we'll get to a bit more specifics on that later on here. But for the most part, what that means is, again, it just means that, each time you go down a period, remember, and as you go from left to right, you're increasing the number of electrons, because you're just also increasing the number of protons in each element. So every time you shift down, you are increasing the energy level, you're increasing the radius as well of your particular element. So, okay, so again, rows, periods, columns, families, or groups. So something else is that we've got to break down, we break down the periodic table based upon orbitals, specifically orbital blocks. Now, we've never really talked about this. I think I've mentioned it once or twice in class, but we've never actually gone through what this is. And what orbitals are, for the most part, and very generally speaking, it's the shape and size of a particular element based upon its arrangement of electrons, or the most probable areas where the electrons will be found on that particular element. And so we can categorize them, and we can put them in all kinds of different blocks. One in the S block, one in the P block, the D block, F block. Now we'll get more into why we separate them into all these blocks, what we can do with that information. We'll get to that later on in Unit 8. But what I want to do is I want to go through and show you where these blocks are and how we can represent that on a periodic table. So here, S block, this is the first two family columns. So this is our alkali and alkaline metals plus helium, and also plus hydrogen as well. So it's going to be the first two columns. So in this block, the last electron is going to fall on the S orbital. Now again, that doesn't really have to make a whole lot of sense now. We're going to try to make sense of that later on in 8.3. Okay, P block. This is going to be families 3A through 8A. The last electron is going to fall on the P orbital. And hopefully you're seeing the trend here. D block, the things that we refer to in the D block, they have the last electron on the D orbitals. And then F block has the last electrons falling on the F orbital. Now notice D block is transition metals, while F block is the inner transition metals. So that's the little spot all the way at the bottom, those two rows at the very bottom, and we can lay it out looking like this. Okay, so everyone should have this. This is a new copy that you would get today of this periodic table. And so what I want you to do is I want you to color in with markers, or with whether you've got markers. Sorry about that. Or if you have markers, or if you have highlighters, go ahead and fill these out. And so you've got the little color coding key down here. But notice, so here's my S block elements right here. Over here, plus helium. Here is my P block over here. Here's my D block, and here's my F block. Now remember, these are referred to as the inner transition metals, remember, these guys are pretty much, you slip them in right here. The periodic table actually bends out like it's basically insert this guy up here and you extend it out. But we put it down here just so you can fit it on a piece of paper for the most part. But anyway, but this is our F block. This right here is our D block, P block, S block. Okay, and again, this doesn't have to make a whole lot of sense right now. We'll get to what this all means later on, okay, in more detail and more specifics. But this is, we're just, again, going through how it is that we can categorize, label, and make sense of the arrangement of the periodic table. So metals, semi-metals, non-metals, I'm not going to go through all of this because what this does is it goes through all the different types of metals found within the periodic table. So there's a position where it that is, or all three of these are found on the periodic table, I should say. So metals are found on the left and middle portion of the periodic table. Okay, and here are their characteristics. Semi-metals, these are the metalloids, the guys that really are metals but not metals, you know, depending on the environment, depending upon the particular time or place that you find them. And they're found in the stair step between metals and non-metals. So remember, it's that stair step that's like right here. So remember, it's like right here. Okay, those metalloids. And then it moves over here, which basically this whole portion right here are non-metals. So these are the far right, are found on the far right side of the periodic table. And again, they can be found as solids, but they're not metals, or they're gases, or they're solids that have a really, really low boiling point, and so they vaporize quite easily, or go through deposition depending on the material. But anyway, in its natural state, I shouldn't say the natural state, a lot of them don't do that, but anyway, but we have the periodic table is broken up into metals, semi-metals, and non-metals. So you're going to need to know this, though. These characteristics you need to know. Metals, where are they found? Okay, what do they have to do with anything? Okay, what do they, as far as ions are concerned, are they positive or negative? Okay, same thing for semi-metals, same thing for non-metals. Okay, you need to know the characteristics for all of those guys. And then the trends. So trends in the sense that when we read the periodic table, it's not just that we arrange them per a particular radius. We don't arrange them because they're just a metal. They have it's arranged in such a way that you can see trends. You can see a pattern of different, different phenomena or different structure. So what I mean by that, I mean that we can talk about, we can actually say, well, from one position to another position on the periodic table, atomic radius is going to change. From one position, excuse the bell, from one position to another position, ionization energy is going to change. And electronegativity is also going to change across a particular direction from a particular position to another particular position on the periodic table. So what are all of these things? So here, let me grab my notebook. So what these things are, for the most part, is within their own names, obviously. So, oh boy, do I have a blank page? I'll grab some scratch paper here. Hold on. So, atomic radius is the distance from the center of an atom's nucleus to its outermost electrons. And remember, those outermost electrons, those are your valence electrons. So atomic radius gets larger going from the top to the bottom of the periodic table, but then the radius also gets smaller going left to right. So let's first tackle what it looks like when atomic radius increases as we go from top to bottom. So if we were to lay out the Bohr model of hydrogen, it would look like this. Hydrogen has one proton in the middle, and it has one electron. It has one electron out in its valence shell. Okay, and I'm going to then go down on my periodic table. Well, let's look at lithium. Well, Lithium has an atomic number of 3, so that means it has 3 protons, so that must mean it has 3 electrons. So it'll have 2 electrons in its first shell, and then it'll have 1 electron in its outer shell. Okay, and then if we go one more down, we'll go to sodium. So sodium has an atomic number of 11, so that means it has 11 protons. So it's got 2 electrons on its first energy level. It then has, let's see here, then it'll have 1, 2, 3, 4, 5, 6, 7, 8 on its second, and then it'll have 1 on its most outer shell. So remember, this is what we're doing here is we're remembering back to energy levels from way back in like Unit 3, bringing back energy levels, and we're using them to show basically the structure of an atom and how that correlates with all the other atoms per its shape and characteristics across the periodic table. So notice, all I did was I went from helium to lithium to sodium here on the periodic table. And notice as we go from top to bottom, what happens is that the atomic radius increases. Okay, so that's to say the distance from here to here is increasing. So look at that, it's increasing. Sodium is like this big, lithium's this big, and then hydrogen's this big. So again, the atomic radius is going to increase in size when we go from top to bottom on our periodic table. But then it has this little guy right here. The atomic radius will get smaller as we move from left to right on the period. So then that I'm sure is starting to make your head scratch, because then you're probably thinking, well, wait, Mr. Sheline, if we're going across here, aren't we increasing the atomic number? And if we're increasing the atomic number, doesn't that also increase the number of electrons that are going to be found on that particular element? The answer is yeah, you will. But the thing is that what's interesting is that as we move from left to right, what happens is that the atomic radius gets smaller, because those attractive forces between the protons and the electrons increases. So as you increase the number of protons and electrons, the smaller it gets, because that force is getting greater and greater and greater. So for instance, let's say for the sake of argument, let's just say for the sake of argument, lithium is going to be this big on the periodic table. And if I keep going on this period, let's take a look. Let's just look at fluorine, or actually let's just look at neon on all the way on the other side. Neon, relatively speaking, would look like this big. It would be like, 1, 2, and neon has a atomic number of 10. So like 1, 2, and then 1, 2, 3, 4, 5, 6, 8. So like neon, because it has, excuse the bell, because it has all of those electrons and protons pulling towards one another, it kind of collapses a bit, and so you don't have as large of a radius. So again, as for atomic radius, as we move from top to bottom, we increase the radius, but as we move from left to right on the period, we decrease the radius. Okay. Now, I understand that hydrogen's not going to be bigger than neon like I show here. It's just relative to this. It's just to say if lithium's this big, this is how big neon is for the sake of argument. Don't think that hydrogen's bigger than neon. It's not. Okay. All right. And then we have ionization energy. So ionization energy is just the energy needed to remove one of an atom's electrons. So this is to say that again, it's the energy needed to remove one's electrons. So the higher the ionization level, the more energy you need in order to bump off a number of electrons. So ionization energy decreases going from top to bottom. And then it increases as you move from left to right. So remember, when we were going over way back when we were first going over ions, and we were going over which ones are more likely to give up electrons. Remember, it was these guys over here that were much more likely to give up electrons, okay, versus these guys, because here's why. So still using lithium over here. Notice lithium has just one valence electron, right? It wants to get rid of that so bad because it would rather be at a more stable state, or at least a more, I guess, even state, maybe we'll say that, a more even state of just the one shell that's filled rather than having this one that still needs like 7. And so then you compare that to, say, fluorine, which fluorine, if I were to draw fluorine here, fluorine, and this is not going to be per size, compared to this, just to kind of show it the same size though, fluorine is going to have 1, 2, so it has 2 electrons, and then it's going to have 7 because it has 9 protons. It has an atomic number of 9. It's going to have 1, 2, 3, 4, 5, 6, 7. And it's got this missing spot. It is one electron away from having a complete full shell, basically being happy. It's missing that one little thing. So it's going to have a higher ionization energy because it wants to gain something because it's so much closer to being stable in that sense. So because it's that close to becoming stable by gaining something, you need a whole lot of energy to break all these guys up. Think about this too, is the fact that you have all these forces between the electrons and the protons. And because there's just more protons and electrons, you just, by virtue of that, you need more energy in order to break that apart. Versus something like lithium that has this one guy out here, and lithium's like, dude, just take it away. Just screw it. You don't need a whole lot of energy to do it. I'll give it to you for free. It wants to have a balance, and it wants to have a full energy level without having to deal with this stupid little dude running around. And something like fluorine will gladly take it. So again, ionization energy decreases as we go from top to bottom on the periodic table. Okay, so top to bottom it decreases, and then it increases as you move from left to right. So again, ionization energy is how much energy you need to remove an atom's electrons. Okay, not one electron, but one of an atom, or I guess it is one of the atom's electrons, sorry. And then there's electronegativity. So electronegativity is an atom's ability to attract electrons in a chemical bond. So electronegativity decreases going from top to bottom on the periodic table, but as you go from left to right, it increases. Okay, and so all electronegativity is, again, is just an ability to attract electrons in a chemical bond. So this is similar to ionization energy. The closer electrons are to the protons in the nucleus, the easier it is to attract them. Okay, so the lower the energy level, the higher the electronegativity. Okay, and then here, elements on the left side of the periodic table typically want to lose electrons to get a full outer shell. Okay, elements to the right side of the periodic table typically want to gain electrons to get a fuller outer shell, and that's basically what I just talked about over here. These guys are going to be not so reactive, though they're going to be more receptive to gaining things. These guys are not so reactive compared to these guys, because these guys are just willing to break those bonds in order to get rid of those electrons, while these guys are not so willing to break apart and not so willing to change their total composition unless they're gaining something out of it. Okay, and so here at the bottom we have a periodic table with all of these ideas. So again, as you move from left to right, atomic radius decreases. As we move from left to right, ionization increases, electronegativity increases. And as we move from top to bottom, atomic radius increases, ionization decreases, electronegativity also decreases. Okay. So what are you going to expect on practicing this? So what you'll expect is something like this. So I don't know, let's say I'll highlight sodium and then I'll highlight fluorine. So between sodium and fluorine, okay, between sodium and fluorine, that's not fluorine, chlorine. Let's say chlorine, forget fluorine. So it's to say that, okay, between sodium and chlorine, which one is going to have a higher energy or higher ionization energy? And we'd say, well, Chlorine is going to have a higher ionization energy, will require higher ionization energy than sodium would. Okay. Or let's say, well, what about boron versus, oh my goodness, I'm blanking on that name, indium. So how do you describe the relationship of boron versus indium in terms of atomic radius? Well, the atomic radius of boron is going to be much smaller than that of indium, just because up here it's going, there's indium has a higher number of protons and electrons than boron does. Okay, well, how do we talk about electronegativity between, let's say, beryllium and calcium? Well, we would say that, well, calcium is going to have a lower ionization level or higher ionization energy than beryllium. Okay, beryllium will have a higher amount. You will need more energy to break apart beryllium than you do calcium. Calcium is much more willing to give away electrons. Okay, so it's basically just reading it like this. That's pretty much all it comes down to, is being able to read the trends of the periodic table. And this really is why the periodic table is arranged the way it is. It's not only just the protons and the neutrons the protons and the electrons changing. It's not just that we just so happen to put metals together. It's the fact that there are very particular patterns that all of these guys show in relationship to one another, that we put them in this order. Specifically, the guy that put them in this order, for the most part, or at least the way we see it today, like this, was Mendeleev. And I'll have some videos for you guys to watch about Mendeleev and, what he was able to do and how obsessive he was about putting, organizing and arranging the periodic table. And amazingly enough, he was able to basically predict a number of different elements before anyone had the tools to discover what they were. And that even includes some of the guys that are down here in this little F block, my little cutoff F block down here. So anyway, so that's what we're going to be practicing. And here I'll grab a copy of the homework. So just to give you an idea. So it'd be like this. So on the homework, here's a question. Which atom in each pair has a larger atomic radius? So for number one, the question is between lithium and potassium. So if I were to look here on my periodic table, I would see that lithium is higher up than potassium. And I know that as we go from top to bottom, our atomic radius increases. So whichever one has a larger one, well, 100% potassium is going to have the larger atomic radius. Okay, another one. Which atom in each pair has a larger ionization energy? So here it's going to be sodium or oxygen. Okay, and we know, as we go from left to right and top to bottom, as we go from top to bottom, our ionization level or energy decreases. Ionization energy increases as we go across this way. So that means that oxygen not only being higher on the periodic table than sodium, also the fact that it is so much farther this way, it's farther on the right side of the periodic table, it's going to have a significantly larger ionization energy than sodium. So we'd say that oxygen has a larger ionization energy. And then the last one here, which atom in each pair has a larger electronegativity? You remember, electronegativity pretty much just follows ionization. Okay, it increases as we move from left to right. It decreases as we go from top to bottom. So cobalt versus arsenic. So cobalt here, arsenic here. Okay, so electronegative, they're on the same plane, so we don't have to worry about that. So really, we just have to look from left to right. And it looks like that arsenic is going to have the higher or larger electronegativity. And it's as simple as that. So that's what we're looking at both for, what we're practicing here in the notes. And then here on the back is a number of different long-form questions to explain which is what and what is which. And that's pretty much it for the notes, guys. So if you have any questions for me, make sure you ask. If not, I'll see you in the next one.